Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom, as you step on inside and we look at more complicated rational functions to graph. Now, what does that mean? The first time that I did a video on graphing rational functions, we were looking at them in graphing form. We had a stretch factor, a vertical stretch factor. We had horizontal and vertical translations, and we could get precise points without even use of a table just by our knowledge of what would happen there. Well, here we're not going to attempt to get them into graphing form. Some of them can't. Some of them could. Some of them can't. But we're going to be consistent with what we try and do and get critical features. We try and get holes, x and y intercepts, vertical and horizontal asymptotes, and then we just try and get middle and end behavior of these graphs. It can be a long process. Even in a best case scenario, these problems are not super fast to do. That being said, you're going to learn a lot about these, and in a worst case scenario, they don't have to be too long either, as long as you can surmise what's going on. Obviously, it's one of these kinds of videos where I can spend a longer time going over the first kinds of problems of this accord. We have 8 problems, by the way, to do with graphs, and there's going to be a PDF down below for this one, so you can graph alongside with me. And it could speed up as you go, but what I need to do is cover each type of problem, because we will possibly get horizontal asymptotes that are on the x-axis, horizontal asymptotes that are off the x-axis, and oblique asymptotes, only of the slant variety, so slant asymptotes as well, which is going to be brand new for a lot of you guys. Now, this is something that I warned about when I was talking about a bigger review of an overall midterm and stating that there are more complicated types of graphs that we can do, and these will be them. So I'm going to go ahead and get started right here, graphing literally more complicated rational functions. These are the things that we want to identify, and they will help us draw this graph, and we may have to get more points than just this. Now, here's the thing I want to state. Although I will get those critical points, I will get exactly where any holes are located, exactly where any x and y intercepts are located, exactly where any asymptotes are located. The other points to me don't matter as much. What matters is where the graph goes. In other words, if I have a drawing vertical and horizontal asymptote like this, I care more as to whether the graph does this versus this than I care about what the actual points themselves are. And that's something that, if you want to find them, plug them into a table. You'll see what I'm going to do using what's called a sign chart to find more arbitrary points if need be. So let's go ahead and get into it. We are going to identify holes, vertical asymptotes, horizontal or horizontal or oblique asymptote, x-intercepts, and y-intercepts of each. There should only be one y-intercept of each. Whatever, that's okay. Then sketch the graph. So let's start with number 1, f of x equals x squared minus 2x over x squared plus 2x. Now, in order to get these things started, I really like to kind of almost go in the order that they provide us here, starting with holes and vertical asymptotes together. It's more so holes first if they're there. And here's what's going to happen. We haven't not done this before. We have done this before. Let's factor the numerator and denominator of these. There's an x common factor to get x minus 2, and an x common factor on bottom to get x plus 2. Now we got an x over x cancellation. Remember, x something over itself equals 1. They don't actually go away. What we're doing is we're going to write a simplified version of this function, and in doing so, we have to acknowledge the fact that x also cannot equal the value that I would have to plug in for x here to divide by 0. Now, what I'm partially saying is I hope that you know something about these graphs. I'm doing more complicated ones, so I sure hope you've seen the ones before. I can't divide 0 by 0. That would lead to a hole if I divide 0 by 0, and therefore, that's where we can identify our first feature. The hole, the only hole that exists on this one here, is when x equals 0. See, if I substitute 0 for here, I get 0 over 0. So 0 comma what? So the idea of the hole, it's not in an actual location, but it does present an actual limit for our curve. In other words, our rational function will actually approach and jump a point and then go there, whatever. So we want to find out where the location of that hole is so we can draw the curve through that particular place. So how do I substitute 0 in for x into this if all I'm going to get is 0 over 0? Well, you substitute it into the simplified version right here. And if I substitute 0 into here, I get 0 minus 2 over 0 plus 2. That's negative 2 over positive 2. F of 0 is negative 2 over 2. which is negative 1. So there is a point on our graph that is 0, negative 1. Now, that also would have happened to have been the y-intercept. Already we can say that there will not be a y-intercept on this, and we'll kind of see as to why that'll be pretty soon. Okay, so there's that. So there's the hole. Now, check on that one. Now, vertical asymptotes. Vertical asymptotes are values of x where we divide by 0. Wait, Mr. Robinson, I thought you just said that's where holes are. Well, it's for both. Domain holes and vertical asymptotes represent our domain restrictions, where we would end up dividing by 0 in these functions. The holes are where you divide 0 by 0. Vertical asymptotes are where you divide non-zero by 0. So now we're looking at the x plus 2. For our vertical asymptote, and there could be more than one, not in this case, but if x plus 2 equaled 0, then that would, that would be a problem. So x plus 2 cannot equal 0, therefore x cannot equal negative 2. So there is going to be a vertical asymptote at x equals negative 2. Wait, I thought you said x couldn't equal negative 2. No, you're right, x can't equal negative 2. X equals negative 2 is the equation of the line where the vertical asymptote is present. And that's what they're asking you to do. Actually draw the equation, draw the line for that. So we are stating what that equation is that represents it. And that's x equals negative 2 right there. So you can't have a point there. And if you know anything about irrational functions from before, it's going to have some sort of approach thing, either that way or that way, something like that. That's why the basic form really helped us figure that out. So there's our vertical asymptote at x equals negative 2. Now, does this graph have a horizontal or oblique asymptote? So what we're going to do here to recognize this, instead of doing long division and getting the quotient, which I will do for oblique asymptotes, and I'll show you why in a bit. We can do it for this, I'm just not going to, is let's look at the original function here prior to any factorization, and let's look at the leading terms. These are both x squareds. And in fact, they're 1x squareds at that. But the fact that they're x squareds, degree 2, being equal matching degrees, means that you will have a horizontal asymptote. And it happens to be at whatever these coefficients are, when you divide these, what is 1 divided by 1? That is the y equals for this. To put this into perspective, what you want to think about is the fact that these x squareds being the leading terms, they are very dominant in this case. You can pretty much ignore the negative 2x and plus 2x when it comes to what happens when I substitute a really large number. I think I have to hiccup. Excuse me. What happens when you substitute a really large number, a billion, a trillion, infinity, positive or negative, into this thing? What's going to happen? And your values will tend to be, really the minus 2 times a trillion plus 2 times a trillion means nothing compared to what a trillion squared is. And 1 times that will make a difference and will make a dent compared to, 4 times that. There will be a difference in those two. So really you're just looking at this 1x squared versus this 1x squared here, that when your numbers get really large, what value are we tending to approach? Now the negative and positive 2x matter with regard to a remainder, with regard to being above or below it. That's why it's an asymptote. We never actually hit it. So it's important to note that we won't be on the asymptote, but the idea is, as long as these are equal degree, the question is how do these coefficients compare? 1 divided by 1 is 1. If this was a 2, 2 divided by 1 would be 2, and our asymptote would be at y equals 2. But this is going to be a horizontal asymptote at y equals 1. And I imagine this isn't the only time you're going to see one with matching degrees on top and bottom. And then we'll see what happens when we have a smaller degree on top and a larger degree on top, whether it's a horizontal, oblique, and where it goes. But that's what we're looking at. That's why it's at y equals 1. And now x-intercepts, should they exist, what I want to do is set the numerator equal to 0. And I can do the factored numerator because I don't care if what happens when this is 0, because that's where the hole is. I don't care about that one. I just care when x minus 2 is 0. Why don't I care about the denominator? Because, hold on, let me write this, VA, this is where we find it. So x-intercept. Why don't I care about the denominator? Because I don't want the denominator to be 0, right? In fact, that's where our vertical asymptote is. But if the numerator is 0, and I divide it by a non-zero number, I get 0. So I'm trying to see, when does x minus 2 equal 0? And again, the more you see me do this, the more it'll hopefully make sense. That's when x equals positive 2. So there is an x-intercept at 2, 0. And I'm going to go ahead and plot that point. That is one of my critical points here. Now, y-intercept, I already mentioned before that there actually isn't. There isn't a y-intercept here. Now, how do we know for sure? How can we tell? Well, there's only one y-intercept ever in a function because there should only be one y for any x value. And in this case, there's no defined y value here because we have a hole. So we know here there's a hole for one. For another, how do we figure it out? Well, we substitute 0 for x. What happens when you substitute 0 for x in the non-simplified version over here? You get 0 minus 0 over 0 plus 0. You get 0 over 0. You get an indeterminate. That is not possible, So there is no y-intercept here. The hole is our representation of that. So, okay, what are we looking at here? We covered everything as far as features go on this list right here. We have the hole, we have the vertical asymptote, we have the horizontal asymptote, we have the x-intercept, established there was no y-intercept, and we have some critical features to be able to figure out what this graph's going to look like. So, how do we figure out what the graph's going to look like? Well, for the most part, you can imagine that this bottom right region is going to have some points through it because it needs to, this hole is a limit where the curve does approach, and it needs to also get closer and closer to that asymptote there. And it's going to get closer to this asymptote by passing the x-axis here and get closer here. Now, I don't know if it's worth mentioning now or not. It doesn't apply here to my knowledge. I'm not actually too concerned with looking at it for now. But there are possible graphs that can jump the thing and kind of curve back down. They have a certain look to their equation to make it happen, and this doesn't appear to really be one of them. So it's possible to do that, but here we're just going to draw and approach it there. Now on the other side, now it's also possible for the graphs to be symmetric in this way and have a curve that do that. But I know that this isn't going to do it without plugging in a point. See, I could substitute -4 for x or -8 for x and figure out what the actual y value is. I'm not going to really care about that. What I do know is that if it came from the bottom, then it would have to approach the asymptote. And if it has to approach the asymptote, then it has to pass the x-axis. And if it passes the x-axis, then it should have another x-intercept. Well, we didn't find another x-intercept on this thing. There was no other x-intercept. If -6 was an x-intercept, okay, then, we would put it there. But we don't have another x-intercept there. So that leads us to believe that it's going to, by nature, instead do something like this and cross through there. Now, like I stated, I'm not getting specific points for you. I'll let you do that on your own if you'd like to, but I'm giving you the general behavior of this graph, which will be the more important aspect for these when we're drawing them. And that's why the critical features are nice to get, right? As long as we can get those ones, and it's by virtue of factoring and simple substitutions, then we do have the good parts of this thing. Now there is a level of symmetry that can be applied to the majority of these graphs, as in if this hits 4 over here, this actually should hit right there. And there's something like that you can do. But I'm going to save that for now. So those are the features that we're going to find in these graphs. I just found them here in number 1. And like I stated, I'll try and speed up on the other ones when it comes to explanation, unless it's a new thing, especially when it comes to that horizontal or oblique asymptote. Or if just the problems are different in terms of needing to find new points. Sometimes we'll have 2 vertical asymptotes, the whole 9. All right, so let's move forward. Let's go down to number 2, where we have f of x equals 1 over x squared plus 2x minus 3. Like last time, guys, it might be worth us to go ahead, well, it is, to go ahead and factor this thing. The top is a 1. The bottom we can factor into x plus 3 times x minus 1. Nothing on top and bottom can cancel, so there are no holes. When it comes to holes, there are none. Holes, none. Because we can't divide 0 by 0. If nothing cancels, then there's nothing to plug in for x on top to cancel something on bottom. Or to divide on something on bottom to make 0. But there are vertical asymptotes, and those are the 2 domain restrictions that we see here. If x plus 3 equaled 0, then x would equal -3, something that we can't have as far as points go, but that's where we draw the vertical asymptote. And if x minus 1 equals 0, then x equals 1 represents the vertical asymptote there. So I will go ahead and draw those for you. That's x equals 1, and x equals -3. Okay, so 2 vertical asymptotes, which does prevent a little interesting case when it comes to what's called middle behavior. We're going to run into that when we see fit. Let's look now at horizontal/oblique asymptotes. What will happen? Well, 1 is a constant. That also means 1x to the 0 power, which means nothing to us except for understanding the top is degree 0. And degree 0 is less than degree 2. So what happens when you have a mismatch here where the top is a smaller degree than the bottom? Well, when the top is smaller than the bottom, I want you to think about a higher degree, meaning x is affected, the bottom's affected more when you plug in higher values for x, like a trillion, infinity, whatever. If I plug in a trillion into this thing right here, this bottom will be massive, and the top will be 1. 1 over supermassive number is pretty much 0. Right? We approach 0 in those cases. And that's what happens here. If the denominator is a larger degree, then you will be approaching 0 on y when you get very large numbers as you approach positive and negative infinity for x. So this is a horizontal asymptote at y equals 0. That is the case for any such times when you have a larger degree on bottom. So this would be horizontal asymptote of y equals 0. This problem, unlike number 1, by the way, could not get in that graphing form that we were so comfortable with. And you can tell it's a very different looking kind of problem with regard to what you have here as well. So don't even bother trying with that. Okay, what are other things we could potentially find? X-intercepts is a possibility. Now, you might say, well, there's an asymptote here on the x-axis. It's not possible. No, as I mentioned, you can cross the x-axis in the middle, you know, like early on. It's possible to get one of those crossing early and doing things like that. Asymptotes, horizontal asymptotes are with regard to end behavior. As you go incredibly large and far down the line, what do we get closer and closer to? And it will be worth us probably doing a long division on something, especially with an oblique asymptote, to talk about how the remainder talks about that. But it's possible to get x-intercepts prior to. Not for this problem, though. If you recall what I said about x-intercepts before, the whole idea is to set the top equal to 0. 1 equals 0. To get an x-intercept, solve for what values of x will make a true statement there. Nothing's going to make a true statement there. 1 never equals 0. That's not possible. There is no x-intercept here as we set the top equal to 0. Nothing to solve for x there. Y-intercept's a different story, though. And the y-intercept, I can go ahead and set x equal to 0. And if you saw what I did last time, I actually plugged 0 into the original equation. And the reason didn't have to do with canceling this and that. It's because this is easier to calculate. See, in factored form, not that this is hard, 0 plus 3 is 3 and 0 minus 1 is negative 1, but you do have to multiply those. And again, not necessarily hard, but look how much faster this is. When x is 0, this term goes away, this term goes away. I get 1 over negative 3. I have nothing to calculate except for the final division, but I have nothing to multiply prior to it. So if you substitute 0 for x into the original, assuming, see, this is assuming it's a polynomial, assuming that it's a standard form written thing where you can just cancel things out by crossing them out. So anyway, you can see that when x is 0, y is negative 1/3. Negative 1/3. So this is at 0, comma, negative 1/3. And you know, there are going to be some fractions in these problems. It is the nature of the beast. That is something that you're just going to have to accept. And I'm hoping that I just did that part right. It looks like it's all good. So that's where we cross the y-axis there. And that's the extent to where we could find pieces to this thing. Okay, where do we go from here? Now, let me talk about, I'll talk about the end parts first. I'll talk about the middle second. Now, we don't have any x-intercepts or holes to talk about. Does this graph go here or here? And does the graph go here or here? This is where we can substitute values. I'm not particular in trying to find out what the actual y value is at a specific x value. What I am particular in finding out is with respect to our asymptote, and this is where long division could be used, but with respect to our asymptote, do we have a positive or negative number? Because our asymptote's on the y-axis, I just care if the result's positive or negative. And if it's positive on one part, say I figure out it's positive up here, then I know I'm going to draw it on this side. Because it doesn't cross the x-axis ever. We don't have any x-intercepts, so I just know that. Same with this here. So what I'm going to do is I'm going to develop what's called a sign chart. Now, I know this is a lot that you're hearing right now. This is why they're more complicated. You can plug in points. Do what you've got to do. This part can go faster if all that you're expected to do is come up with the end behavior, the general look of these graphs here. A sign chart is going to do this. I'm going to draw basically a number line, and on this number line will represent any x critical features that I do have. Right now, for me, it's just vertical asymptotes, negative 3 and positive 1. If I had x-intercepts or holes, I don't know if holes matter. If I had x-intercepts, I would consider them as well. And the reason is because those are times where you can potentially change sign on your graph. If I had an x-intercept right here, yeah, it's possible that it goes from positive to positive like that, but it's more likely it's going to go from positive to negative. And I want to know on one side of the x-intercept am I positive or negative, and on the other side of the x-intercept am I positive or negative. Same thing with these asymptotes. This thing might go toward negative infinity right here, and on the other side of the asymptote it might go toward positive infinity. So what I want to do is know what's happening to the left of negative 3, in between negative 3 and positive 1, and to the right of positive 1. And whatever's happening there is likely happening for the rest of that graph. Otherwise, we would have crossed the x-axis. Otherwise, we would have had another asymptote. So that's the idea of the sign chart. So what I'm going to do is I'm going to substitute a number, and it doesn't really matter what the number is. What matters is you knowing how it compares to your equation. And you can use the simplified version of this, by the way. So let's use an example like -5. Let's plug in -5 for x into here just to get the idea. I don't care about what the numbers are. So here's how the sign chart thing works. If I substitute -5 in here, what I'm going to get sign-wise is a positive number on top, because 1's a positive number. And then on bottom, I have -5 plus 3. Again, I don't care what the answer is, I just care what the sign is. Is -5 plus 3 a positive or negative number? What's negative? Is -5 minus 1 a positive or negative number? That's negative. Negative times negative is positive, and positive over positive equals positive. So on this side right there, on this side of -3, I should get positive values. I don't know what the actual number was at x equals -5. I just know that it's positive on that side, and it should remain that way. There's nothing to indicate that there should be any sort of change in that, because there are no more intercepts, there are no x-intercepts, and there are no more vertical asymptotes. And that's probably what your graph's doing. Are the exact points there? Let's try to the right of 1, positive 1. So f, and by the way, I'm not going to write all this each time. I'm going to retain it in my head and say it out loud more. In fact, let's do a little bit of that now. F of 1 is a positive number, so I get positive, over 1 plus 3 is positive, and, excuse me, I don't want to plug in 1 itself, let's plug in 2. 2 plus 3 is positive, and 2 minus 1 is positive. Positive over positive times positive is positive. So we get a positive result to the right of 1 as well. And the same thing that I just did with that other side there, I will get here. So I substituted in 2. And once again, it kind of makes sense on the graph as well. But in the equation, when I talked about -5, see, what's going to change if I try a number like -2, which I will try, versus -5? -5 plus 3 is a negative number, but -2 plus 3 would be a positive number. So some little signs change because you're on one side or the other of -3, which affects, how things change up. So what's between -3 and 1? I could try 0. You know what? We already do have a value here. Let's go ahead and say that. We tried 2 here. We'll try 0 here, and we do have a value, and that is negative. We got -1/3 there. Sometimes you should try more than just one value. This time you don't need to. Like I said, it's possible that graphs can go through and do this. It's possible they can go through asymptotes here. But I would have known that if I had an x-intercept here, and I didn't. There was no x-intercept here, so it's going to be impossible for me to cross this barrier. And the way that these dotted line vertical asymptotes work is that you approach negative infinity in both those directions from there. So this graph is doing something. I don't know exactly what it's doing, but it's doing something like approaching negative infinity there, and it turns back around right around here, and it's approaching negative infinity right there as well. That's the only way that this graph features these bits right here and maintains everything about it that it is we need. The sign charts apply correctly. Try and plug in -2, see what you get sign-wise. And there we go, that's the graph. So once again, very long explanations for these things the first time that you're hearing them. It's hard for me to not talk about them that way, but these can go speedily, not like 2 minutes speedily. It depends on the problem, I guess. These will take a moment for you to get every little consideration and possibly a sign chart involved, and we haven't even talked about oblique asymptotes yet. So it just depends on what you're given and what you can do with the information. That's why these are more complicated rational functions. All right, I got 6 more to go, and they shouldn't go as long unless we have an oblique asymptote. Be forewarned, it's possible we're looking at one right now. Number 3, f of x equals x squared minus 1 all over 2x. Okay, so this graph right here, let's go ahead and try and factor. We do have a difference of 2 squares on top to turn this into x plus 1 times x minus 1. This is all over 2x. Now, nothing canceled. So did this help us? And nothing factored on bottom. So did this help us? Yeah, because it'll help us for finding x-intercepts. It'll help us when we are doing sign charts and all that. So let's first talk about holes. There are none. No holes. Because nothing canceled. Vertical asymptotes, there will be one, and it is at x equals 0. Again, when you consider that you are dividing, when you plug in 0 for x, you'd be dividing by 0. That's where it is, which also points to the fact that there is no y-intercept on this graph. We'll plug it in and see what happens there, but there's no y-intercept here. What do I want to do next? Horizontal or oblique asymptote. Okay, so now let's look at the original thing here in standard form and compare x squared over x to the first power. Now the numerator is larger than the denominator. Now it's larger. Now this one takes precedence. This takes hold. What happens when I plug in a trillion for x up here and down here? A trillion squared trumps anything times a trillion all day. Well, maybe not a trillion and 1 times a trillion, but as you get larger, infinity, negative infinity, whatever. Now, it doesn't mean the number gets largely positive every single time. It could be largely negative, but the idea is it doesn't approach a single constant value. It approaches positive or negative infinity in one direction or the other. Let's find out, though, because this is not a horizontal asymptote. It's an oblique asymptote. Let's find out what that asymptote looks like, and let's approach the asymptote from there. So this is what I want to do. I want to use long division on this. I'm going to go ahead and to find out the oblique, not the oblique, we're going to make a simplified version of the, we're going to make a different version of this thing by dividing x squared minus 1 by 2x. We got to find out how many times 2x goes into x squared. And this one's not as fun to do. X goes into x squared x times, but 2 goes into 1 1/2 times. Okay, 2x times 1/2 x is indeed x squared. And you subtract those, you get 0 there, and then -1 minus 0 is -1. So the quotient to this thing is 1/2 x. The remainder to this thing is -1. So a rewrite of this equation is f of x equals 1/2 x is the quotient, and then 1 over 2x is the, oh, that's weird looking. 1 over 2x is the remainder, right? 1 divided by this guy here. Now that's the remainder there. Okay, so this, let's see if I can, I don't know if you'll be able to make sense of this. All right, in one tell. All right, so this is the quotient. This is the whole thing's the remainder. All right, here we go. Y equals quotient is where the oblique asymptote is going to be. The oblique asymptote is actually just at y equals 1/2 x. Now, the reason for this is because you will never, unless there's middle behavior where you cross it because of, intercepts and whatever, long term, you will never actually touch this line. Because what happens is there's this part right here that even if you plug in 100 for x, you'll still be 1 over 200 minus 1 over 200 underneath that line. If you plug in a trillion for x, you'll be still 1 over 2 trillion underneath that line, or possibly above, all depending on negative a trillion, things like that. You'll never actually be on the line. And that's what the remainder does. It gives you a little bit off of it. And that's how asymptotes work. They say we get really close to this thing, but then you subtract a little teeny bit of it right there, or you add it, or you do whatever, and then you're never actually on it. But we got to graph y equals 1/2 x, which is starting at the origin, we rise 1, run 2, rise 1, run 2, rise 1, run 2, etc. And then fall 1, run 2 this way. So we're going to draw this line right here, and this is what we approach here. This is an oblique asymptote. Now, oblique is a general term for anything that's not horizontal. So it could be, this one specifically is called a slant asymptote. It's possible to get quadratic ones, like this. We're not going to be doing those, or a cubic or anything like that. It just depends on how the numerator compares to the denominator. This is just 1 degree larger, so we'll have a 1 degree linear asymptote there. Okay, so our graph is either going to do this, or possibly in that, or possibly this and that, or maybe some version of this and this. There's something that's going to be happening there. We have to keep going with our intercepts as we continue forward. So we have no holes. We have a vertical asymptote at x equals 0. We have an oblique asymptote at y equals 1/2 x. We got that by actually dividing this and determining the quotient. The quotient ends up representing the oblique asymptote in and of itself, because the remainder keeps you off of the asymptote itself. It says we approach it, get super close, but never actually hit. Now, x-intercepts, we set y equal to 0. So x plus 1 times x minus 1, we set y equal to 0 and say when does the numerator equal 0. So when does this equal 0? Use the factored form. Zero product property says that x can either equal -1 or x can equal +1. So there is an x-intercept at -1, 0. There's an x-intercept at 1, 0. That's good. We got a point right here. We got a point right there. And that is very, very telling of what our graph is going to do. It's extremely telling of what your graph's going to do with regard to location and such. Now, y-intercept, we established previously that there isn't one. And the reason is because you have a vertical asymptote there. Make no mistake, it's impossible to cross a vertical asymptote because the vertical asymptote is telling you that there can't be an x value there. Horizontal and oblique asymptotes talk about end behavior on x, so middle behavior could have that happen, but not in these other cases here. So our graph, because these x-intercepts here, our graph is telling you here that we are going to be approaching from here, hitting that, and then curving down there. I gotta probably make this one a lighter shade of purple or something like that so you can really see it. And then on this side here, we'll be doing that. And I don't really need a sign chart, to tell me this stuff. Ugh. That's good enough. But that is a good idea of the graph right there. I'll keep it like that. That's a good idea of the graph right there. I don't really need a sign chart to tell me what's going to happen on these. Now, here's the thing. Sign charts are a little tough to talk about right now because the idea is you're not checking to see if something's positive or negative anymore. Well, sort of. You're not going to check in the original function because if you find out the sign's positive, well, it could be above or below the asymptote still, right? How do you know if it's above or below? You would test the remainder. And let's test it. Let's plug in 1 trillion for x. What would happen is you'd have -1/2 trillion. So you'd have just underneath the asymptote. If you plug in -1 trillion, you get +1/1 trillion, which is just above the asymptote right there. So a lot of new stuff. 3 different problems with 3 different things to talk about there. And hopefully the rest of the problems kind of have something else in conjunction so I can be a lot speedier, a lot hastier with the process. 3 problems in 32 minutes. I bet I can still get this done in an hour, assuming that nothing else is way out in left field compared to something else. I know there's one thing we still haven't hit, which is in between 2 vertical asymptotes when we kind of go through, or how do we figure out whether it goes through or not. We'll get to that with sign charts. All right, number 4. F of x equals. Now, what I'm going to do when it comes to factoring is let's go ahead and first factor a negative out of the top to get x squared minus 16. And then on the bottom, let's factor that out right to x plus 4 times x plus 2. And then the top factors into x plus 4 times x minus 4, another difference of 2 squares. On bottom, we get x plus 4 times x plus 2. And we have x plus 4s that can go bye-bye. Now those will represent the x value for our whole. Excuse me, the simplified version of this whole thing is that. You can put distribute the negative in or leave it out. It's kind of your call on that, but I'll just leave it like that. So this is the simplified version of this thing where we can figure out things like x-intercepts, we can use sign charts on these, we can do asymptotes, yada yada. Vertical asymptotes. Okay, so let's start with the holes, or hole in this case. Just a single hole at x equals -4. That's where you'd get 0/0 pre-cancellation. Now, what is the y value? Substitute -4 into this equation right here, f of -4 there, and you will get -4 minus 4 is -8, over -4 plus 2 is -2. So +8 over -2, which is -4. So -4 for x, -4 for y. And that is right here. So I have a nice big gaping hole right there. The graph is somehow going to go through that curve. I have no idea what this graph's going to look like except for just that part right there. All right, vertical asymptote, that is where any non-whole domain restrictions equal 0 in the denominator, of course. So vertical asymptote. X plus 2 can't equal 0, so x can't equal negative 2 down here. So x equals negative 2 is the vertical asymptote. So it's right here. There's our vertical asymptote, and one and only. All right, horizontal oblique asymptote. Well, we have matching degrees, even matching degrees, so ignore the rest here as we try and divide simply negative 1 by positive 1. Negative 1 divided by positive 1 is negative 1, so we get a horizontal asymptote at y equals negative 1. And to humor you with this one is actually possible for us to have gotten into that old graphing form. And I want to talk about it right here just to compare it to, let me draw this really quickly here, just to compare it to what we did before and what, like in a couple months ago, and what we did on just problem number 3 when I talked about the quotient representing the asymptote, horizontal or oblique, and the remainder representing whether you're above or below, because we might need it to test more points. Because we now can't just use a sign chart and determine whether something's somewhere unless we have x-intercepts and we can tell for sure where something's going to be. So I'm going to go ahead and divide. This is negative x plus 4 if I distribute that. So negative x plus 4 divided by x plus 2. This isn't something you're required to do, all depending on the problem. Sometimes you should, sometimes you shouldn't. X goes into negative x negative 1 times, so we negative x, negative 2 times negative 1 minus 2. And this gets you a remainder of 6, because 4 minus negative 2 there. So your equation can also be written as, and remember, this is the simplified one when the x plus 4s were canceled. Negative 1 is the quotient, and then it's plus 6 over that x plus 2 right there. Now, in graphing form, I would say, hey, here's your a over x minus h plus k, and we would do something with that. And we very much could just graph this together, right now. But to keep it consistent with everything else we're doing, what I want to make mention of, here is your quotient. This guy here is the quotient. The quotient represents your horizontal, or your asymptote. This is your horizontal, your asymptote's at y equals negative 1. And negative 1's a constant, so it's horizontal. This is the remainder, and the remainder helps tell you when you will be above or below your asymptote based on certain x values. If I plug in a huge positive number for x, I get a positive result, which means we'll be just above the asymptote. So you're never negative 1. You're never negative 1 because you're always going to be adding 6 over something. So you're never negative 1. You're just above or below it. When you're positive, you'll be just above. When you're negative, like negative 100, that'll be 6 over negative number. That's just below the asymptote. So I already know my graph's going to be somewhere here and somewhere here. But I still have a y-intercept and x-intercept to find. And let's go ahead and do that. Okay, so let's move forward. The x-intercept, I'm going to set y equal to 0 with this top. When does negative x minus 4 equal 0? Well, when x minus 4 equals 0. And when does x minus 4 equal 0? When x equals 4. So 4 comma 0 is x equals 4. So 4 comma 0 is our x-intercept. And then your y-intercept, we set x equal to 0. And I'm going to use the original right here. And 16 over 8. Y-intercept is at 0, 2. 16 over 8 is 2. We get 0, 2 right there. I don't need a sign chart. I don't need this long division remainder stuff to tell me what it is that I know about. This graph's going to be on this side, and this graph's going to be on this side. So I can go ahead and draw that. If you really, really, really wanted to use what we did in old school ways, you could say, hey, what's 6 divided... Do you remember this? What's 6 divided by 1? That's 6. 6 up from the asymptote. 6 divided by 2 is 3. 6 divided by 3 is 2. That would be there. 6 divided by 4 and 5. 6 divided by 6 is 1, and that's where you get that point. So if you remember that old school stuff, we do have this in graphing form if you actually wanted to use that. I'm not requesting that we use that, and we can't always get into that graphing form with these things. I can't seem to get a good looking curve out of this one, though. Maybe it just naturally does have that sharp curve. That's right. And, there would have been symmetry on this side. 6 over negative 1 would have been negative 6. 6 over negative 2 is that negative 3 whole. 6 over negative 3 is negative 2. 6 over negative 6 is negative 1. So this side would have had this approach here. And again, if you can get it in graphing form, great. A lot of these will not. I wouldn't be surprised if the rest of them do not at all get into that graphing form. All right, so there is your graph for number 4. A little bit more of the stuff with holes. Let's go forward. All right, number 5. F of x equals. Let's start by factoring out the negative on top. And we get x squared minus 3x minus 4. On bottom, we have a difference of 2 squares of x plus 3 times x minus 3. And on top, I can continue by factoring with that negative outside to x minus 4 times x plus 1 over this x plus 3 times x minus 3. All right, we factored but nothing canceled, so there are no holes present here. So what can we say based off that? Well, there's a lot more information here. We're going to have 2 vertical asymptotes. We'll have 2 x-intercepts. We're still going to have information to work off of here. So let's go ahead and get started. Holes, none. Vertical asymptotes, there are 2 of them at x equals negative 3 and x equals positive 3. So I'm going to start with those 2. All right. Vertical line, that wasn't even close. Vertical line at x equals positive 3 there. And then another one here at x equals negative 3. Okay. You're lucky we're not doing any oblique asymptotes with, what was I going to say? Parabolas and things like that. Those get crazy. They're just crazy to look at in general here. Okay. Vertical. Okay, horizontal asymptote or what? We got a tie. We got a tie here, so ignore these. We're just looking at negative 1 over positive 1. Hey, we've seen that before. That's going to be at y equals negative 1. So we have a horizontal asymptote at y equals negative 1 because of the tie. Okay, now let's start looking at intercepts. Let's look at x-intercepts. We set the numerator equal to 0. So x can either equal 4 or negative 1. That's x equals, whoops. So 4 comma 0 and negative 1 comma 0 are our 2 x-intercepts. So negative 1 comma 0 is here, 4 comma 0 is here. Y-intercept, there can only be one if it exists, and there should be because we don't have vertical asymptote or hole restrictions. What we do is we set x equal to 0 here, gone, gone, gone. We get 4 over negative 9, which is negative 4/9. So 0 comma negative 4/9 represents the y-intercept. So that's like here, negative 4/9. It's, you know, kind of like there-ish. And there we go. We're good on that. All right. Trying to decide if it's worth, okay. So I'm going to do long division on this thing to kind of bring forth that sign chart idea, because you can do this one of 2 ways. You can either plug in points. Well, actually, you know what? I somewhat take that back. I somewhat take that back. Okay, here's what I'm thinking about. Okay, where do we know that the graph's going to go here? We know that because of this x-intercept right here, that we have a good inkling that we are in this region right here for this graph. Let's see. I know what to do with this. I just want to know how to talk about it with you guys here. So we have that part of the graph. And we also know that because there's no x-intercept here, that there's no way that the graph's approaching through there because it doesn't cross the x-axis there. So we know on this side, it's going to be coming up and through, this way. That's really not a good looking version of that graph, I'm sure. It's probably going to hit somewhere like there. But that's the general nature of the curve. If we want to use long division to figure out end behavior, we could. What we really want to do is build a sign chart around the middle, because we don't know whether this, well, actually, no, yes, we do. I was going to say, we don't know whether this graph, there's one thing we don't know about this graph. We don't know whether this graph, see, we do know that the graph cannot do this because it should have hit another x-intercept if so. But we don't know if the graph either does this or does the slight possibility of potentially doing this, where it hits and just goes up there and then goes down there. I doubt that's going to be it, but you know what? I don't know. So here's what I'm going to do. I'm going to substitute negative 2 for x, and I'm going to figure out whether this number is positive or negative. because it can either hit from up there or it can hit from down there, either one or the other. And hopefully you understand what I mean by saying I know it can't do that, because there is no other x-intercept or hole or anything right here that shows that it's going to do that. So just understand, this horizontal asymptote is not impervious to being crossed. It will be crossed. This thing is going to be approaching down below like that. Will it be coming from up top? That's my guess that it will. Will it be coming from down below? It's possible, but my guess is it won't. So let's find that out. Let's substitute specifically -2 for x into here. F of -2, and all I care about is sign. So we have a negative times -2 minus 4 is negative times -2 plus 1 is negative over -2 plus 3 is positive times -2 minus 3 is negative. Negative times negative times negative is a negative. Positive times negative is a negative. Negative over negative is a positive. So -2 results in a positive number. Whatever it is, could be fraction, could be 1, I don't know. Whatever it is, it's a positive number. That means that on this side, it's going to be up top. So it does come from up here as it then falls through the graph and then curves down below and does feature stuff like that. So this should be the appearance of the graph. It's really sketchy, as it is a sketch. It's a really sketchy kind of look to this graph, but that's what we're going to be doing there. There could be potential reason why we might do long division on this thing. Check out the remainders, compare on top and bottom, and see, did this graph jump over or something like that. You know what? I'll do it for this one just so I don't have to do it for later ones. So let's try and do -x squared plus 3x plus 4 divided by x squared minus 9. That goes to -1 time. I'm not going to spend time talking about the math I'm doing here. It would be 3x minus 5. And then that can't go into that. X squared can't go into this. So 3x minus 5 is your remainder. So your whole thing is now f of x equals -1's the quotient, and then plus you have 3x minus 5 all over x squared minus 9. So what you would do here is, obviously -1 represents the horizontal asymptote. What you would do is sign charts on the remainder. You would try and you could factor x squared minus 9 into x plus 3x minus 3, as we did before. X plus 3x minus 3. It might make things easier when it comes to signs. What happens when you substitute -5 into this thing? You get a negative up top over a negative times a negative. So negative divided by a positive is a negative. So you're underneath the horizontal asymptote on the left side. On the right side, you know what? I'm kind of taking back what I'm going to say here. Actually, you know what? It is a good thing we did this. I'm looking at, is there a chance that we can get this thing to hit? Well, I shouldn't have erased that. Is there a chance? Oh, never mind. I see it. Okay. One of the questions besides sign charts is, does this ever cross the asymptote? I think that's the more important question to us, not what side is it on. We knew it wasn't on the top side because it never hit an x-axis. But the bigger question involved is, does this ever cross the horizontal asymptote? The same way that we did x-intercepts before. The same way that we did x-intercepts before, setting the top equal to 0 right here and solve for those x's. Now we're setting the remainders numerator equal to 0 to say when we cross the x-axis. And that's something you could find. It's going to be, the point that's right there. So when does this equal 0? At x equals 5/3. So really that actual point is like right here, whatever, where it actually crosses and goes through. There's no other time that it crosses though, right? There's no other 0 for this remainder that says it crosses through. So it doesn't cross through here. It doesn't cross through here. So that is the graph. Okay, that is the graph. Sign charts wouldn't be necessary for that as long as you know it doesn't cross, and that's all we need. All right, a lot of stuff to talk about there. Let's keep moving forward to number 6. F of x equals x squared minus 2x minus 8 over -3x minus 3. You know what to do. Let's factor x minus 4 times x plus 2 on top. On bottom, you can factor -3 out, and you're left with x, what is that, plus 1. And there's nothing to cancel, so that's going to be our result of that thing right there. So we start with holes, none. Holes, there are none. Vertical asymptote, we'll be at x equals -1. That's the one where we would be dividing by 0, and we don't want that. So that's going to be at x equals -1 right there, our only domain restriction. Horizontal or oblique asymptote, we're going to have an oblique asymptote this time. We have a larger degree on top than we do on bottom. Let's do long division to figure out what the equation of that line is going to be. So I'm going to go ahead and take x squared. See, it's not -1/3. There's something about -1/3 with this, but we'll figure that out. X squared minus 2x minus 8, all divided by -3x minus 3. -3x goes into x squared, x goes into x squared, x times, -3 goes into 1, -1/3, whoops, -1/3 times. -3x times -1/3 x is indeed x squared. -3 times -1/3 x is positive x plus x right there. And let's subtract. These go away. -2x minus positive x is -3x. And we get -8. And -3x goes into -3x one time. So you multiply those, we get -3x minus 3. And we subtract that out, and we get -5 right there. So -5 is the remainder. -1/3 x plus 1, because -3x can't go into a constant, right? So your quotient, your division, your divided version of this is going to be quotient of -1/3 x plus 1. That's going to be our oblique asymptote. And then our remainder is -5 over -3x minus 3. I'm going to write this version, -3 times x plus 1. Factored form is fine. I don't know which one's preferred there, because do we need that factored form anymore? I don't think it's necessary that I care about sign charts here. What did I mention before? As long as it's not a whole, I just care whether or not it crosses again. And it doesn't seem that it will. You know what I do want to do, actually? I want to factor a -1, because I don't like double negatives here. I'm going to factor a -1 out of there, and then I'll turn that double negative into a positive. There we go. I know I'm probably going above and beyond what you guys would know to do there, but that makes things easier when it talks about remainder being above or below the graph, something like that. All right, over 3x plus 3. Okay. So this guy, the quotient, -1/3 x plus 1, is our oblique asymptote. This is y equals -1/3 x plus 1. All right, x-intercepts. So you can see, even in a fast-paced, it's not fast-paced, but even in best-case scenario, these problems aren't necessarily quick to do. Oh, -1/3 x plus 1. Let's graph that. So y-intercept of 1, and we go down 1, right 3, down 1, right 3, and up 1, left 3, like so. So our graph will take on this appearance right here. Okay. X-intercept, or intercepts, should they exist. Let's see. We set the top equal to 0. You can have 4 and -2. So 4, 0, -2, 0. So -2, 0 is here. 4, 0 is here. Gives you a good heads up of what it looks like this graph's going to do. One more mention on this. If I mentioned the remainder before, if you set the numerator of the remainder equal to 0, you can tell that 5 can never equal 0. So there's never a time where our points will ever cross this asymptote right here. Therefore, we know that we're going to be on this region up here and this region down here. There's one thing left to get, which is the y-intercept. So I'm going to set x equal to 0 here. Boom, boom, boom. We get -8 over -3, which is positive 8 over positive 3. And 8/3 is also 2 and 2/3. So we'll be up 1, 2, and 2/3 right there. There's the y-intercept. Okay, we have enough for a graph. It is going to be hitting here. It's going to be approaching here. And the asymptote there. And on the other side, it's going to be hitting here. And the other side like that. And that is our graph. Okay, so you can see where a little more speed is coming into play here. I have 2 more problems here. Ooh, only 6 minutes till the hour. I guess I won't get there. I slowed down a little with the long division talk and talking about how I wanted to teach you how to best do some of those. All right, number 7. Let's factor a -3 out from the top. You're left with x plus 4. Let's factor this into x plus 3 times x minus 2. Once again, nothing to cancel. We've been without holes for a while. Maybe number 8 will present us with holes. Vertical asymptotes. There are 2 of these. There's going to be at x equals -3 and x equals, I don't need the positive sign, x equals +2. +2. So let's go ahead and do those first. X equals -3 and x equals +2. Okay. Asymptotes, you have a larger x-intercept, you have larger degree on bottom, so this is going to be at y equals 0. There will be a horizontal asymptote at y equals 0 right here. So it's going to be going across right here. That's not to say there aren't x-intercepts. It's still possible to have them, especially in middle behavior, such as, here we go, x-intercept. You can indeed set that numerator equal to 0. If -3 times x plus 4 equals 0, then x plus 4 equals 0. And if x plus 4 equals 0, then x equals -4. So -4 comma 0 is your, oh, it's right here, is your x-intercept. Okay. -4 comma 0 is it. So you notice here, this one's crossing horizontal asymptote. I want to make sure I did everything right with that, but it's crossing horizontal asymptote right there. Didn't expect that. So a sign chart will be completely relevant for this problem when we do that. The y-intercept is something we can still find, though, by setting x equal to 0 here, here, and here. We get -12 over -6, which is +2. So 0 comma 2 is a point that we have as well. Okay. So we have as many points as we could come up with there. Now, we still need to know whether the graph will be on this side or this side. It looks like this graph will only be on this side right here. Otherwise, we would have had an x-intercepts that would have told us to go through. And this one's a little different because this is either, to me, it's either going to be coming from up top and down here and then back through, or the other way, like that. And it's a little confuzzling to talk about with regard to that because you might be confused as to why that happens. But knowing there's an x-intercept there means it has to cross, and it also has to approach the asymptote. So the question really becomes, what happens to the left of -4? What happens in between -4 and -3? We can, I don't think it's worth checking on other values. We already know what it's going to do here. It's got to approach from here, otherwise it would cross the x-axis here. I didn't make a mistake in my factoring, right? That's -3 times x plus 4. Yeah, that's good. And +3 and -2. Yeah, okay, just making sure. And then what happens to the right here? So let's build a sign chart here, basically a number line. And let's do any critical points, such as -4, -3, and +2. We want to know what happens in between these. Between -3 and +2, it's going to be positive. We can kind of establish that based on this. I think it's fair to say that the graph, we don't know how low and stuff the graph goes to hit certain parts. I'm not testing those. I'm not getting actual points. I never was, except for intercepts. But we know that it's not going to be hitting the x-axis because we would have otherwise gotten an x-intercept there. Okay, so there's that. Let's see what happens to the left of -4. Let's go over, let's try a number like -5. So what you're going to get is a f of -5. You'll get a negative in -3 times a negative. -5 plus 4 is a negative number right there. Negative over negative divided by a negative times a negative right there. That's positive over positive, which is positive. So to the left of -4, it's going to be a positive result. That means it probably comes up above this thing to then flatten out on the asymptote there. You try another negative number even farther down, it's going to still stay positive because these will all end up the way they are. Now between -4 and -3, you have to do something like -3.5, and that's not too fun to talk about, but you'll see why this, like I'm not calculating, but you'll see why this one's going to be a little different. -3 is a negative number. -3.5 plus 4 is a positive number. Like that would be positive 1/2. But -3.5 times plus 3 is still a negative number here, and this one's negative. You can see now this sign changed once we're in between. That leads you to a negative over a positive, which is a negative number. And so this gets a negative here. So what's happening is this thing is below right here, and then it goes up and through. I don't know how high it gets up to. It does something where it has to cross, and then it goes back down and approaches through as time goes on. I'm not looking for relative maxima and such with you guys. that's neither here nor there for us. But this is one of those really bizarre graphs where it's like I'm not plugging in a bunch of points to the table to figure it out. I know based on signs where things are going to go with that. Now, it's not going to do that on this side here because otherwise we would have had another x-intercept. But what does happen here, let's plug in like 5 over here. We do negative times positive over positive times positive. So negative over positive is negative. So we're going to get a negative right there on that side. Again, that's me just doing, 5 plus 4, 5 plus 3, 5 minus 2. Just getting the signs there. And I get negative, which means we will be underneath on this side as well. Now, this will stay underneath the entire time that we're over here as it approaches closer and closer to the asymptote. And that is this graph. Very, very tricky, even without holes. Very, very tricky on that graph, especially with that part right there. All right, we have one more to do, and that is number 8. Oh, man. All right, number 8. We have a common factor of x on top, and then we can get x squared minus 7x plus 12. Whoa. We have a common factor of negative 4 on bottom, and we're left with x squared minus 3x minus 4. So continue factoring these quadratics. This will leave us with x minus 3 times x minus 4. And on bottom down here, we'll have x minus 4 times x plus 1. All right, the x minus 4's cancel. We will have a whole at x equals 4. And let me write the simplified version of this first. X times x minus 3 over negative 4 times x plus 1. Okay, we'll have a whole at 4 comma, let's see. This will be 4 times 4 minus 3 is 1. So 4 over negative 4 times 4 plus 5, negative 20. So 4, was it 4? 4 over negative 20 is our f of 4, which is negative 1/5. So 4 comma negative 1/5 ends up being our whole. That's right, really close to the x-axis, right there. Okay, so we have that. Make sure all my math was right there, I believe. Yep, believe it was. All right, vertical asymptote. Just at x equals negative 1, now that the 4 part is gone, so x equals negative 1 there. That is right here. Okay, the oblique or horizontal, this will be oblique. When you just ignore these, you look at the rest. I got a cubic on top and a squared on bottom. So let's do long division. Let's do long division on this thing. Can I do, am I allowed to do long division on this simplified version? I am. It's fine. I didn't do it in the others because it, was already factored, and this is as well. But let's just go ahead and distribute into that. So that's x squared minus 3x over negative 4x minus 4. Okay, let's divide right there. X squared minus 3x over negative 4x minus 4. So negative 4x goes into x squared, negative 1/4 x times. So let's multiply those, and we get x squared, of course, there. And negative 4 times negative 1/4 x is positive x. Subtract, and we get negative 4x from here. Negative 4x goes into negative 4x exactly one time. And negative 4x times 1 is negative 4x, and minus 4 here. I'm subtracting. This is 0 minus negative 4, so that's a positive 4 here. So my end result of that now is going to look like f of x equals negative 1/4 x plus 1, and then the remainder is plus 4 over negative 4 times x plus 1 there. So this is our oblique asymptote. It is at y equals negative 1/4 x plus 1, like that. So here's our plus 1, and then down 1/4. Oh, look how close it gets to that known point that we have. Oh, this was a hole, wasn't it? That shouldn't be a big, that should be a, there we go. Look how close it gets to that hole. Because it approaches, our hole approaches the asymptote, right? And then down 1/4, and then up 1, left 4, up 1, left 4. So we should have a horizontal asymptote that's looking, an oblique asymptote. It's looking a little bit like that. Now, one of the heavier talks from before is looking at the remainder here. Is it possible for the numerator of the remainder to equal 0? No, it's not impossible it's not impossible for 4 to equal 0. So we're never crossing this asymptote at any time. That means we know this is going to be on this side, but what's the x-intercept, what's the y-intercept? I want to figure that out. And we know this is going to be on this side. Well, no, we don't know what side this is going to be on yet. If there's an x-intercept over here, then we know what side it'll be on. But we know what side it'll be on when we figure out our x-intercept stuff. So let's do that. X-intercept, you set y equal to 0. Set the numerator equal to 0. When does x times x minus 3 equal 0? Either when x equals 0 or when x equals 3. So we have 0, 0 and 3, 0. Now, if 0, 0 is one of your points, that's also your y-intercept, folks. There's no way around that. You know, you can try it. Set x equal to 0 here. You'll get 0 over 16, which is 0. So if your x-intercept is 0, 0, then your y-intercept is 0, 0, and vice versa for that. So there's that. All right, so we know what this graph is going to do. We know that on this right side right here, that it is approaching from the bottom. It's going to cross through the origin there. Approach the bottom, cross through the origin. It's going to come up and hit here. It's going to go through the hole. It's going to jump the hole, I should say. It's going to jump the hole and keep approaching closer and closer like that. That's pretty much what it is. Now, we're not coming from this side because otherwise we would have had an x-intercept to tell us that, and this never jumps the asymptote, so that, therefore, this is going to be on this side right here. Probably a lot worse drawn because I didn't get any specific points on it. And that is it. Okay, these were pretty tough. I don't know if you understood everything that I mentioned when it comes to these graphs here, because they can get pretty out there. That's why I just wanted to run the gamut and say, here's what's going to happen, here's what's going to happen. I'm sure I'm with you up until we talk about oblique asymptotes, remainders being just above and below. But I'm sure that with regard to factorization, understanding our features and what's expected of you, there's that. When I do some review stuff, I'll cover more problems like these, but they are more complicated for sure. There's something to them that's a little bit different. And I'm not stopping you from using a table, but you got to recognize you're going to have a lot of fractions if you do that. And you have to make sure you still cover the gamut when it comes to what's going to happen on one side of an asymptote and another. That's why sign charts are very nice when you feel you need to use them. All right, that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.